All right, team. Now we're going to do an example that uses a log normal distribution. And previously, we defined the log normal distribution as a skewed distribution that only has positive values. So if x is log normally distributed, then it's probably going to have some kind of shape like this, where it's got this long tail, some extreme values, and then a lot of values in the smaller realm. And for this example, we're using some data taken from a study, early study that was published from data from Wuhan, China, where the coronavirus was discovered. And they found, based on observational studies, symptoms, and that sort of thing from thousands of people, that the incubation period for the virus, defined as the time from infection to onset of illness. So when you get infected by someone, breathing in their air or whatever, and then to when you become sick and show symptoms, that incubation period has a mean of 56 days and a standard deviation of 28 days, and that it is log normally distributed. That's the distribution that best fits the distribution of incubation periods. So X is our incubation period, and we'll just write that out real quick. And we have a lot of kind of shorter incubation periods. So the mean is somewhere around here, about 5.6. And then there's that standard deviation of 2.8 days. But we do still have a lot of longer incubation periods over here. So the first thing we're going to do is to calculate the parameters of this fitted log normal distribution. And these are the log normal parameters. So these parameters right here, this is ux, or you could say x bar is 5.6 days, and then sigma x is 2.8. And now we want to calculate mu y and sigma y, which are the actual parameters that go into the log normal distribution. So this is just a basic plug and chug. We get our equation for mu of y, and that's equal to the ln, the natural log of mu of x, minus 1/2 sigma y squared. And then we also, before we can calculate that, then we need to calculate sigma y. I always start out with mu, mean, but in this case, we need to start off with sigma. So sigma y is equal to this bad boy here. We've got the log, natural log of 1 plus sigma x over mu x. So this is the coefficient of variation, right? Squared. So we can calculate that first, and we'll do that, and then we'll plug in the other values. So our sigma is 2.8 days divided by 5.6, square that, and then we'll pop that in our calculator, and we come up with 0.47. And now we'll calculate mu y, which was ln of mu x 5.6 minus 1/2 0.47 squared. Plug that into our calculator, and we get 1.6. All right, so those are the interim parameters that we'll be using for this log normal distribution, and that we'll be working with for subsequent problems. All right, so let's take a look at the next part of this. That was not too bad. The next part says, all right, so what's the incubation period in days below which 95% of incubation periods fall? So this is the probability that x is less than or equal to some value that we'll find 0.95, so the 95th percentile, right? 95% of the observations fall below that. So the probability that x falls below that is going to be equal, by definition, 0.95. So essentially, we can turn to the cumulative distribution function. But we'll just draw this out. We've got our log normal distribution. And we're trying to find some value of x, we'll call it x.95, such that the area under the curve up to that point, so the probability is the same thing as the area under the PDF, that area is equal to 0.95. So this is our PDF. And then we'll also look at the CDF. Big F of x. And this is going to be a little bit different than your symmetrical normal distribution. It's going to have kind of a quicker rise earlier on, and then it's going to flatten out and have kind of a longer tail down on this side of things. And so this is our x95, which comes all the way up to here. And then that's going to give us, of course, that's nice and straight, right? That's going to give us a value of a cumulative probability value of 0.95. Great. So that's what we're looking for. And we know that we can use our phi function, which is the cumulative distribution of the standard normal variate. But there's just a slightly different definition of the standard normal variate when it comes to the log normal distribution. But essentially, this is what we're going to be solving. We're going to be solving z and ultimately x to find that value of the incubation period in days. So this is our 95th percentile. So we can look this up, and we've looked this up before. The z value associated with a cumulative probability of 0.95 and the standard normal variate is equal to about 1.65. All right. And that is either from a table in your book or from Q norm and R. And we plug in 0.95 and it spits out that z value associated with that cumulative probability. Great. So now we can know that here's the z value that we're going to be solving for. Let's just write out the equation that gives us the standard normal variate for the log normal distribution. So ln of x minus uy all over sigma y. And this is kind of the crux of it right here. And what it says is that if a log normally distributed variable follows a normal distribution if we take the log of it. So here is the distribution of our incubation periods, which is log normal. And then we can say that ln of x follows a normal distribution with these parameters, mu y and sigma y. So this is the kind of key relationship here that we're using. And then we can solve for the standard normal variate for a log normally distributed variable by taking its natural log and then doing that transformation, except instead of mu x and sigma x, we're doing mu y and sigma y, which we previously solved for. All right, so not too bad. So we'll just solve for x. So ln of x is equal to z sigma y plus mu y. And then we get x is equal to exponentiated z sigma y plus mu y. All right. Now we'll plug in our values and we can say x is equal to e to the 1.65 times, that was 0.47 plus 1.6. And then finally, we get that 95th percentile incubation period, 10.75 days, or we'll just go ahead and say 11 days. You know, if we're issuing guidelines based on that, we're going to say, okay, 95% of incubation periods are less than 11 days. And so that might be some, you know, isolation period that we would use. So it says, okay, you know, as long as you're not symptomatic after 11 days, then there's only a 5% chance that you still could be and have the coronavirus. All right, last thing that we'll do is find the probability that the incubation period is greater than 14 days for an infected individual. So you're infected with SARS-CoV-2, with COVID, but you still have this long window before which you might exhibit symptoms before that incubation period ends and you're symptomatic. So that we know that 14-day was the initial kind of quarantine and isolation rules when the pandemic kicked off. So what we're looking for is the probability that X is greater than 14 days. And because we're using greater than here, that's important because the CDF only gives us less than or equal to. So we can say this is equal to 1 minus the probability that X is less than or equal to 14 days. All right. This is like going to the cumulative distribution function. And if we have 14 here and we have our cumulative distribution function, this will tell us the probability up to 14. But now we're, instead of calculating that, we're going to calculate what's above that by doing the complement. So let me just extend this a little bit. So here's our 14. Whatever this probability is, we don't know. And the cumulative distribution function gives us everything up to that point, but we just want basically this probability up to 1. And so that's the 1 minus the probability that's less than. So it's just that little bit that's left over. A little bit of probability that's left over between 14 and essentially when this cumulative probability goes to 1. All right, so let's think about this. We have our CDF. This is basically a cumulative distribution or cumulative probability that we're interested in. And so we can go back to phi here and say this is phi of whatever the z value is at 14. The standard normal variate for 14, given the parameters of this distribution. So this is the same thing as saying the probability that's less than or equal to 14. It's the probability of phi, the cumulative probability at whatever this z value is, which we don't know what that is. But we can calculate Z14 very easily. We don't have to go to any tables. The Z14 just represents the transformed value of 14. So in this case, X is equal to 14. We want to get the standard normal variate for the log normal distribution. So we're going to take ln of 14 minus mu of y all over sigma y. All right, and then we calculate that and we end up with a z value of 2.21. It's a pretty big z value. Remember the 95th percentile z value is 1.65. So we're way above that at this point. Now we can plug that z value into phi, into our original probability equation up here. So this is going to be probability that X is greater than 14 is equal to 1 minus phi of 2.21. And then we can look that up in our table, or we can just go 1 minus p norm. So this p norm is the cumulative probability distribution function for the normal distribution. And if you give it a z value, it's the standard normal variate. Those are the default values in R. And so we can just give it a z value, and it will give us our cumulative distribution function value at that particular z value. So that ends up being 0.9864. And so our probability then is 0.0136. So about 1.3% of cases have an incubation period greater than 14 days. So that 14-day period, you know, it's fairly conservative. It captures just under 99% of the cases for this particular distribution and for this data set, right? This is one data set. And certainly as the pandemic's progressed and with vaccines, things have changed quite a bit, but that's where that original number came from of 14 days.